Hello dear friends, this is Pradeep Kumar from FEMA Engineering Solutions. I am a mechanical engineer. Here I am going to discuss with you finite element analysis techniques. Basics, actually we will discuss today only basics of finite element methods. Actually I performed multiple types of analysis like fracture mechanics analysis, fatigue analysis, and uh, finite element analysis, and vibrations, thermal, and non-linear analysis in fracture mechanics. You know that for getting JR curve we need Ramberg-Wood equations, and that equations itself is a non-linear equations. But here it is just more or less, it is just introduction about myself. Now I am not going to deep discussion about finite element method. I am going to discuss with you finite element method at a very basic level, but it is, I have seen that in at most of the cases this part is left. Then I have realized that before getting started to the finite element method, as students must know this. Student must know. So, what is that thing? And that is what is the matter that is important, that we will discuss here in a very elaborate manner. Generally, people start teaching in a finite element method from Galerkin method, weighted residual method. Then they moved for minimum potential energy method, a form stiffness matrix, and globalization of the stiffness matrix, and reduction of the stiffness matrix, and then getting final solution, and stresses, strains, and all these things. But is it okay? I think student must have knowledge about that why discretization, why globalization. It is exact function of the finite element method. Where it is actually reduces the effort that is important to us. So I am going to first discuss with you three basic definition. First is the physical system, second one is your mathematical system or mathematical model, and third one is the finite element model. We will understand physical system, we will understand mathematical model, we will understand finite element model, then solution of the finite element. Any existing system is a physical system. Like very simple example that you have studied at your graduate class in your solid mechanics subjects, like truss, beam. Okay, so we will so truss and beam is a physical system, we can say that, like roof, like electric tower. Okay, so these systems are like columns, studs, these are the physical system, like beams. So these are the physical systems, and what we do, we transpose this physical system into mathematical model. How? Using differential equations. Any physical system can be modeled as a mathematical model using partial differential equation or using differential equations. Now we will understand these things using a very simple problem like beam bending problem. In beam bending problem, let we have a beam and it is a simply supported beam. One end is hinged, another end is hinged and roller. So this type of beam is known as simply supported beam, and load is applied at the center of the span. Okay, so we want to get the deflection of the beam at the midsection. So how do we get? First, we have to convert this physical system into a mathematical model. The mathematical model is d square y whole dx square is equals to m by ei. This is a differential equation. Y is the, what is y? Y is the deflection. Okay, at any point from x is equals to 0 to x is equals to, let L is the length of the beam. I want to get the solution of this equation, and I want to get the maximum deflection. Where is the maximum deflection and what is the maximum deflection value? So we need a boundary condition. So such type of problem is known as boundary value problems. So you know that how to solve this such type of problems. You will just integrate it, and you will put the boundary value, and because this is a second order of differential equation, so you will have two integration constants C1 and C2, and you will put the two boundary conditions, and finally you will get this C1 and C2, and you will put, and you will get the equation of y, and if you put x is equals to L by 2, then you will get y max. Finally, it is simple. It is simple, and you need not to worry about such type of problems, because you are able to solve this differential equations. You can solve this differential equations under certain boundary conditions. Now this is now here you will see the major challenge in the mechanical engineering, aeronautic or automobile or any solid mechanics types of problems. Or we can say that in general form, any solution of any physical problem, I will see problems. I'm saying that we have a lathe machine, and it is running at a certain RPM. So the stresses will be developed in the machines, and also stresses developed in the samples for which lathe machine is there. Like you want some turning operation. So turning operation is actually material removal operations. Material is removed by a CRS process. So samples as well as machines feel stresses developed in their body, and also temperature is also increasing the sample, and also tools, machines. Okay, the temperature of the tools or samples is increasing. Machines will also, the deflection of the machine is, because machine is not rigid, so the deflection is also must be there, something like that. Now if I will say that I want to get the temperature distribution in the turning sample, or in the cutting tool, or we want to get the deflection of the machines at a certain point. So now you will see how to get that. because there is no as such standard equation or in the form of second order differential equations and like that in beam problem. There is no as such like this, and also solid mechanics will fail because solid mechanics has a certain assumptions that plane section should remain plane. You know that? Then theory of elasticity will play a very important role, and when theory of elasticity came into the picture, then differential equation will be made for a particular or for any type of problems in solid mechanics. Then that I want to get the temperature distribution in tool or in samples, turning sample, or a deflection at any point in the machine component. So what we can do, using theory of elasticity, we will form a differential equation. Because this is a physical system, we will make a mathematical model for this physical system. We will form a mathematical model using differential equations, and to get the desired field variables we need a boundary condition, as you have seen in the beam theory equations. In beam theory, at x is equals to 0, if it is simply supported, then you know that y is equals to 0. At x is equals to L, also y is equals to 0. It means this is a boundary condition. If there is a two constants, then you need two boundary conditions. But if your differential equation is in terms of fourth order, fifth order, then there would be 4, 5, 6 number of constants would be there. The number of boundary conditions definitely would be there. So boundary conditions would have been also written in the form of partial differential equations, and mathematical models can also be written in the partial differential equations. Both are written. So how it could be solved? It is very difficult to solve. Not only difficult, we are unable to solve such type of problems. Definitely. Yes, definitely. So then the next thing is that how to solve this partial differential equation under a certain boundary conditions. This is called boundary value problem. So people realize that we are not able to solve this differential equation, complex differential equation. So can we solve it under certain assumptions, certain approximations? People thinking on this side. Then what people did? People assume a polynomial equation for that differential equation. Okay, and the order of polynomial is up to you. It means how to choose. Order of the polynomial is up, this is only up to you. If you let deflection of the certain component is going under cubic and you have taken square, so there would be some error. Okay. So people tried and they solved such complex differential equations using polynomial equations. So polynomial equation can be solved very easily. You know that if it is a naught x plus a1x plus a2x square plus a3x cube, like that. So if you will put the x boundary condition value, or you can form it a matrices form, equation can be written into the simple equations can be written into the matrices. So by inverse putting this value, you can easily get the values of a1, a2, a3, and finally you will get the value of y. If it is terms of y and y is your field variables, so it means you have avoided to solve the differential equations using polynomial equations. Now, I think where polynomial equations, concept of polynomial equations is used, it is used in finite element method. The first step is in the finite element method used to assume a polynomial equations to interpolate the displacement in the body. So what is the definition of the finite element method? Finite element, the definition is that it is a technique, or we can say it is a numerical technique that is used to solve the partial, or we can say to solve the differential equations using polynomial equations. So simple way, FEA is a technique to solve the differential equation. Okay. So need not to be confused about the FEA. FEA is very simple, and you must know that why FEA is used. So this is the reason why the FEA is used. Then your next question should be, why discretization? So we can take one polynomial equation. Why we are taking number of elements? We take one element, and then get that field variables. Why we go for the discretization? Then its answer is that one polynomial equation is not sufficient to interpolate the deflection or deformation of that particular component. So if you will say increase the power, okay, if you increase the power, then what will happen? The flexibility or degree of freedom will increase. Flexibility in the polynomial equation will increase. So control will decrease. So it will be something zigzag type of pattern will be there. So you cannot get the exact. So let deflection is like that and polynomial equation is just fluctuating like this. So again this is a problem. So how to resolve such type of problem? We just make a more number of polynomials. How we can make more number of polynomial equations? By making more number of elements. If we will make more number of elements, it means we are making more number of polynomial equations. So one polynomial equation would be restricted for a very small distance. If you are using 2 mm by 2 mm element size, then that polynomial equation will interpolate for 2 mm element, and another polynomial equation will interpolate other 2 mm. But all these polynomial equations must be continuous. This is very important characteristics. And the parameter which governs all these things is called shape function. Shape function is actually derived from these polynomial equations. So finite element method is a method that is used to solve the differential equation or partial differential equations by a polynomial equations. So equivalent polynomial equation is formed with the boundary conditions for a given partial differential or differential equations, and this is solved by certain boundary. The boundary condition is given, so we will put boundary condition, then we will get constants, then we will put the constants in the polynomial equations, and finally we will get an equation in terms of n1 x1 or we can say that n1, if it is u is equals to like that, so at each node there would be displacement u1, u2, u3, so we will get n1 u1 plus n2 u2 plus n3 u4 like that, and n is the shape function. After u we will get strain. Strain is, you know that it is a derivative of displacements. In the 2D problems, strain is actually del u over del x, del u over del y, and gamma xy is del u over del y plus del u over del x. So this is a strain. So after getting u, so we will just differentiate. We will calculate this del it, and then we will get strain. Okay, so if you see, so we will get in terms of B matrix. So after that strain we get then the f is equals to kd equation is solved, and d is determined. D means displacement at u1, u2 is determined, and after that we get stresses. Sigma is equals to E into strain, and strain is equals to, it is derived, this is B into D. B is the B matrix, D is the displacement matrix. So then if it is generalized, then E will be replaced by stress matrix, that is a capital T, and B is the B matrix, this is strain displacement matrix, and D is the displacement matrix. So this is the equation of the calculation of the stress. So in this way the stress, strain and displacement is calculated. So here we understand that the importance of the finite element method or finite element analysis is that the main importance is that it actually reduces effort to solve such a complex differential equations. We need not to solve such a complex differential equations. We need to solve only linear equations or cubic equation or anything. okay, under a certain boundary conditions. So I think you have got the sufficient point what actually I am trying to deliver to you. So the next lecture would be on Galerkin method or weighted residual method, and then we will start then 1D analysis. In 1D analysis we will see truss beam, then we will see 2D analysis. In 2D analysis we will see plate bending problem, shell problem. In 3D we will, and also we will see the properties of the stiffness matrix and shape functions and the continuity of the shape function. All these things we will see. Okay, and also we will see how any commercial codes could be written, and how the code is running back end of that commercial software. We will also see. So I hope you have got my points, what I actually today I am trying to deliver to, and what was my motive for this lecture. So I think FEA would be easy for you after having all the lectures. Okay, so thank you very much for giving so much time for this lecture. Okay, if you think that it is useful, then you can subscribe it, and for more information you can log on to www.femacanalysis.com, or you can give a message to us, or for any problem info@MECHANALYSIS.com. Okay, thank you.